So tonight we're going to talk about convolution, and unfortunately there's no way to get familiar with convolution without getting dirty, and that means you need to go back through and rederive the results in here. So, most of you are probably saying, well, I'll probably never need this, and you may be right, you may never need it, I don't know, but in the event that you do, we at least want to introduce the variable rate and variable pressure drop convolution. Every time you use a well testing package in one form or another, either the variable rate or the variable pressure drop convolution is being used. Generally speaking, it's almost always the variable rate convolution or the variable rate superposition. Whenever you hear the word convolution, it means integral, and whenever you hear the word superposition, it usually means summation. So the other aspect of this is that this really complicated mess that we perform in the real domain, these two equations that you see here, this being the variable rate convolution or discrete rate changes solution, and then okay, sorry. Did I? Okay, sorry about that. Okay, so in a snapshot, the variable rate convolution or the variable rate superposition is in the upper box, and the variable rate pressure drop is in the lower box. And as I mentioned, generally speaking, when we're looking at an integral, the integral is what we call a convolution, and the summation is what we call a superposition. It doesn't really matter, the nomenclature. I know these variables are unfamiliar to you. You see a PWD, and that means the variable rate wellbore pressure, and then you see a QTD, and that's the total rate from multiple pressure drops. So that's the sort of way we're looking at that. Now, questions or comments about this? The problem with these summations is that every single time you use it, you have to go all the way back to the first point. So if you have an n that is the number of changes is equal to 3, then you do 1, and then you do 1, 2, and then you do 1, 2, 3. But every time you have to go all the way back to the start. There's no accumulation of terms. The convolution is represented by a reference going all the way back to the start. So this becomes very tedious. When you're running a superposition or a convolution or a variable rate or variable pressure drop case in a computer program such as Topaz or Harmony RTA, then you'll notice that it slows down as the calculations become further along on the page. And that's because this is what's happening, is there's an accumulation of terms, and that accumulation is just as bad for the first term as it is for the last. It doesn't get any easier. In fact, it gets more difficult. So there's a cheat. Does everybody know what the cheat is? The cheat for convolution or superposition is that we go into the Laplace domain. We use the convolution identity in the Laplace domain, and you can see it's given below those results. I know you're tired of the Laplace transform, but trust me, it is your friend. Okay, so there's the Laplace transform of the convolution. So I need you to communicate with me and tell me, well, that looks easy, Tom. Yes, it does. And what it allows you to do is it allows you to take the Laplace transform of the rate function and the Laplace transform of the pressure function and convolve them as a multiplication in the Laplace domain. Sounds easy enough, right? Except what's waiting for us? Sorry? Inversion, that's correct. We have to get out of the Laplace domain. And I think we would all agree that that's not a pleasant prospect. So we have two choices. We can work in the real domain with convolution, or we can work in the Laplace domain with convolution. Generally speaking, we always work in the real domain because it's more straightforward and we don't have to deal with inversion. And inversion costs just as much as performing the other operations. Now, below it, you see something that says Laplace domain result. And it's important to realize what that is. That's the constant rate and constant pressure relationships. So Van Everdingen and Hurst, the way they did this is they took the solution for constant pressure and the solution for constant rate, and they set them equal to each other, and this is the result they obtained. But this result can be derived directly from the convolution. They didn't know that. In fact, I didn't know that until I took a class. Actually, after I graduated with my PhD, I sat through Raj Raghavan's class, and he showed an approach of how to do this. And I've completed that approach in this work. So there's a derivation of how to develop the Laplace domain result. There's also a real domain result, as you see below, where the real domain result is that in the real domain, this integral equals time. So you can set this real domain result up as a recursion relation, which is really painful, because what happens with recursion relations? Recursion relations are like summations. You have to go all the way back to the front in order to get an answer. What else is bad about recursion relations is they're not stable. They do not like error in the results or in the data. Of course, we're talking about analytic functions here, so there shouldn't be too much of an issue. But if you tried to apply this to a real function, it probably would give you an issue. So this variable variable pressure, the constant pressure, constant rate Laplace domain result comes in handy when you want to derive one solution or the other. Okay, so now we work our way towards deriving the the variable rate convolution case. And in this case, we have a simple set of steps that look like this. We have a rate step 1. It's given here. We have a rate step 2, which is here. We have a rate step 3, which is here. And then we have a last rate, which is rate step 4, and it's here. This is very straightforward. I think you would all agree there isn't any real challenge to this. And the pressures that follow that are here. And those pressures pretty much do whatever they want corresponding to the rates. So the first rate is big, and when we change the second rate to be small, obviously the pressure builds back up. And then we have a third big rate, so the pressure goes back down, and we have a fourth small rate, so the pressure goes back up. All of these things I'm trying to demonstrate. Now, the first rate, its convolution, or its differential here, is simply Q1 minus Q0. What is Q0, class? Q0 is 0. And then we have the second one, and it's Q1 minus Q2. And you'll notice that's a negative number because Q1 is greater than Q2. And then the third one we have is Q3 minus Q2. And of course, we're positive again. And then we have Q4 minus Q3, and that's a negative again. Okay, so somebody asked me, why are we doing this? Well, this is the way that it's formulated. We're looking to calculate the total pressure drop for each step. So we have the first pressure drop is given as, I know you can't see it underneath here, but it's PI minus P1. The second pressure drop is P1 minus P2. The third pressure drop is P2 minus P3, and so on, dot, dot, dot. Okay? So that's how we think about the pressure drops. So we're going to add them all up. In order to do that, we make ourselves a reference rate, and we look at how we change over a given interval, and we write out expression number 2, and then we work backwards and we write out expression number 3. We're going ahead and do some algebra there. And this gives us the pressure drop across each step. So equation number 3 is the pressure drop across each step, relative to each rate and the time over which it's applied, and there's a reference rate thrown in there for good measure. So when we add all the pressure drops up, we get equation 4, and that's where our convolution or our superposition comes from. And I know some of you are thinking ahead, so if we take the differential of the rate change to be really small, let it go to delta Q go to well, it'd actually be delta Q over delta T, go to 0, we then get the summation form. Everything below this, equation 5, 6, 7, 8, 9, they're all about converting equation 4 to a dimensionless form. But equation 4 is the form we would use if we were going to make certain kinds of calculations, like in a simulator. Okay? Then once we're done, we have equation 11, and equation 11 gives us a dimensionless pressure form for this result, and you can see it's written in terms of dimensionless rates, and in this case this is just the rate divided by a reference rate, and then it gives us the dimensionless pressure evaluated over the convolution time, and that's given there. Now that dimensionless pressure is the constant rate dimensionless pressure. Okay? So now we're going ahead and we'll work through, we'll multiply through by a differential. We'll define a differential and then multiply through by it. And you can see when we get down to the bottom where we have equation 12 that we're looking at this formulation. And this is certainly valid. There's no loss of generality here. This is a delta Q over delta tau and then a delta tau multiplied there. So what happens is when we take the limit as delta tau goes to 0, this becomes an integral. And that's where equation 13 comes from. And then when we apply the dimensionless form, we get equation 14. There is another form of equation 14 where we're talking about a pressure derivative instead of a rate derivative. That's sometimes referred to in the literature, but for the most part, you're going to see equation 14 referenced in its present form and used in its present form. So are there any questions or concerns about the application of variable rate superposition or variable rate convolution? Equation 14 would be the convolution. Equation 11 would be the superposition. Obviously one is discrete and the other is continuous. Any questions, concerns, frustrations, anything like that? Okay, that's the real pressure drop, not the dimensionless pressure drop. That's the real pressure drop for the constant rate case. So the ordinary dimensionless pressure that you're used to using is PSD. When you multiply PSD by these terms, like this, you get delta PSCR. Okay? That's where that comes from. So that's a real domain form, and the other is a dimensional, or sorry, it's a field variable form, and the other is a dimensionless form. You're going to work in the dimensionless variable form. You're going to utilize these kinds of formulations. I don't know if you're looking at slide 1 again with me, but you're going to utilize these kinds of formulations. You're probably not going to work in the dimensional or in the field units form. Okay? So from now on, I would suggest you familiarize yourself with being able to derive this. This would be a very good thing for you to do, being able to derive equations 4, 11, 13, 14. Okay, now I probably should stop the lecture here and just go on to the wellbore storage case, but I know everybody wants to know something about the variable pressure drop case. The variable pressure drop case is actually easier in some ways than the variable rate case, but it's confusing because of the way that we set this up. It may not be more confusing to you because you're not accustomed to it, but bear with me. Okay, so there's our first pressure. Here's our second pressure. They're held constant. Here's our third pressure. And then here's our fourth pressure. So those are our pressure steps. And then the rate, on the first one, it sees, okay, I've got a constant pressure at the wellbore, so my rate's just changing. And then it has to bounce up. And then there's another constant pressure, but it's lower, so the rate has to be higher. And all of these, of course, are cartoons. Each individual well model would give a different signature, but I'm drawing this out in this fashion. Sometimes these tools, Okay, well, hopefully that gives you an idea of what that'll look like. And then we have to do the same sort of stepping thing where we take and we calculate the pressure difference at each step. And of course, the first one is the difference between PI minus PWF. The second one is PWF1 minus PWF2. The next one is PWF2 minus PWF3. And then the next one is PWF3 minus PWF4. So it's sort of a similar stepping system. The easier part here is to understand that the total rate is simply the addition of all the individual rates. So that's fairly easy to understand. We set up a similar mathematical relationship as we did before, that we have a relationship between the actual rate and the actual pressure drop, and then we have a relationship between the constant pressure rate and the pressure drop according to that reference condition. And that ratio sets us up to where all we do is solve for Qj, and then when we do that, we simply add up all of those rates. So just as I suggested, we multiply the pressure drop from the other side, so now we're looking at PI minus PWF, PI minus PR, multiplied by the constant pressure solution over a particular convolution interval, and then that's our rate over that term. So then we simply add up all of those rate terms and their corresponding convolutions, and that gives us equation 19. Okay, so equation 19 is similar to before. That's our discrete stepping equation for estimating the total rate based on a variety of pressure steps. Now, equation 20 is the cumulative production rather than the rate, and it's simply constructed as the cumulative production instead of the rate. It would be the integral of 19, and then we convert all of this to dimensionless form. And that's what everything else working through this part of the derivation is going to give us. Until we get to equation 23, which is the total dimensionless rate in terms of the incremental constant pressure dimensionless rates. Okay? So this one is a bit more abstract, but what I want you to understand is every time you hit the button to say go in an analytical simulator to calculate a variable rate pressure drop or a variable pressure rate case, that's what this is generating. And it uses equation 19 or it uses equation 22, however it's constructed, and that's how it calculates the different functions. These are not model-dependent results. These are analytical, completely rigorous definitions of variable rate and variable pressure drop cases. These equations are exact. Let me put it that way. Okay, what's the problem with exact equations, class? Exact equations always work, that's nice, but they require the data that you use in them to be correct. There's also another issue that all of these solutions or all of these results depend on the differential equation that created it to be what? To be linear. It needs to be the liquid differential equation. So how would you utilize these equations for gas? Anybody want to guess? Nobody's going to guess. Okay, what would happen is you would have to reformulate these problems in terms of pseudo-pressure and pseudo-time. And I skipped that part in the exam, but if you're going to use pseudo-time, it would have to be material balance pseudo-time, and it would have to be calculated on a known volume, which is okay because as long as you're doing steps in rate, so variable rate steps, that'll be known. You'll know the cumulative reduction, so you'll know the pseudo-time. The problem comes in when you're doing variable pressure steps, and then you'll have to iterate. Okay. Stepping through the next parts of this, I'll leave this for you to review on your own, but this is the result I was talking about earlier, where you're able to define the relationship between constant pressure and constant rate solutions. This is the development of the exact identity using convolution on how to transform this convolution into a relationship that describes either the constant rate solution or the constant pressure solution in the Laplace domain in terms of each other. So again, I'll leave that for you to review on your own, but if you're ever in a situation where you need to know the constant rate solution and you know the constant pressure solution, then this is the derivation that shows you how to relate in between there. Actually, what's going to happen is you're going to want the constant pressure solution and you're going to have the constant rate solution, and you're going to have to use these results to go between those, and that's exactly what their main application is. So stepping through this, you can see that we do derive the Van Everdingen and Hurst result at the end. It's equation 45. Okay. And then the last thing that we would talk about would be this aside over here, that we can actually integrate these results and get a relationship that describes the convolution between the constant pressure and the constant rate cases. And you can solve this as a recursion relation if you would like. Okay. So this is a very heavy, very theoretical lecture. There's not a lot of simple things in it. The only way to understand this material is to get dirty with it. This is one of those tools that you're going to leave in your toolbox and never take out until you really need it. But when you need to understand variable rate problems, come back to this lecture. I'll repeat all that. This is a very, very specialized tool. But when you need to understand variable rate or variable pressure solutions, come back to this lecture. Everything in here is completely documented. It's obviously correct. It's obviously exact, etc. These are identities. There's not a, there's no approximations. There's no nothing. These are all rigorous identities, mathematical identities. So if you ever needed to use them, here they are. I'm going to stop for a moment and save this video so it's only for the convolution, and then I'm going to bring up the wellbore storage video. Are there any questions before I do that? Okay.